Hello students. In previous lecture, I have talked about the boundary points of subset of metric space, and we have derived equivalent conditions for finding the boundary points. In this lecture, we will talk about the topic distance between 2 points, distance between point and set, and diameter of subset in metric space. So as distance function is defined on metric space, so distance between any 2 points is defined, and that's why it is possible to define distance between point and set, then distance between two sets and diameter of set, etc. So you are much more familiar with distance between line and a point in plane. What you are doing, you are drawing a perpendicular from that point to the line, and that perpendicular distance is nothing but distance between line and point. For circle, also you are doing same thing. If I have two circles, if they are intersecting, distance between that two circles is 0. If they are touching, their distances between that two circles must be 0. And if they are not intersecting, then what you are doing, you are finding distance between their centers, and then you are subtracting sum of the radius of that two circles to get the distance between that two circles. So this is the way of finding distance between two sets. Now who can define it mathematically in metric space? So if XD is a metric space and AB are non-empty subsets of X, then distance of any point X in X from set A is given by, so we'll compute its distance of X from every point of A, and among all distances which gives us the smallest value. But this smallest may not exist. Right? Then in that case, instead of smallest, we will take infimum. So d of xa is equal to infimum of d of xa. A value is in A. Is it clear? Then distance between two sets A and B is given by, for circle what I have told, what you are doing, you are finding radius, then distance between their centers, and you are subtracting sum of the radius from that distance between two centers to get the distance between circle. What is it exactly? If I compute distance between any 2 points of that set, where one is from A and the other is from other set B, and if you take infimum of that, that infimum defines distance between that two sets. Diameter, for circle diameter is 2 times radius, etc. But for any arbitrary region in R2 xy plane, how we can find diameter? So with respect to that D function defined on metric, we will compute distance between any 2 points in that set. For any 2 points, and then supremum of that is known as diameter of the set. Diameter may be infinity. Is it clear? But distance of x from given set is always finite number. Distance of point from given set is always finite number. Now by observation, if this x in x is member of A itself, the distance from x to x, where x is in A, is 0. Means among all distances 0 is also there. Means distance of any point of given set A to that set is always 0. Or distance of a point x in x from matrix space X is always 0. Distance between two sets A and B now. If I have A and B are intersecting sets, then there is a common point, say x in A and B both, which is member of A and B. Then treating that x as a point of A as a point of B, d of xy, d of xx will become 0. So if A and B are intersecting sets, then distance between A and B, two sets must be 0. Distance between that two sets must be 0. Diameter of A. Now if I take the open ray A to infinity as a subset of Ru, set of real number with usual metric, then distance of A from every point, if I compute, as value of x goes on increasing A infinity, x, so distance between distance x approaches towards infinity as extending to infinity. And therefore diameter of open interval A infinity or minus infinity to A open ray or whole metric space Ru is what will be diameter? Infinity. But if I take close interval AB, open interval AB, open close interval AB or close open interval AB in usual metric space, then what will be the diameter? Diameter is exactly B minus A. Diameter is exactly B minus A with respect to usual metric. Now if I take the discrete metric space in which d of xy is 1 and for x not equal to y and it is 0 for x equal to y. Then if I take empty set or singleton set in discrete metric space, its diameter is 0. And if that subset A contain at least 2 points of that set, metric space, say A contain x and y where x is not equal to y, then distance between that 2 points is 1. If I have any number of points, so if I take any A set containing more than 1 points as a subset of discrete metric space, then that diameter of that set must be 1. And diameter of any subset of A, of metric space XD is less equal 1. And a metric space is said to be bounded if diameter of every subset of metric space is less equal some fixed number. There doesn't exist a subset of metric space whose diameter goes to infinity. Then in that case we will say that metric space is bounded. Similarly, subset A of X metric space is bounded if diameter of that set is finite number. So this about these things. Now we'll prove one theorem depending on distances. So from previous lecture I am writing results on the board. Okay, firstly, because it saves our time, let XD be a metric space and AB are non-empty subsets of X. AB are non-empty subsets of X. Then d of AB less equal d of distance between A and B sets is less equal distance between any two points AB where A lies in A and B varies in B. This result is too simple. D of AB is nothing but infimum of D of XY where X varies in A and Y varies in B. This must be less equal to D of AB for any A belongs to A and B belongs to B by definition of infimum. By definition of infimum or greatest lower bound of set. Set of D of XY is subset of close open interval 0 infinity in R. In R. And that's why we are talking about whether that is bounded or not. So A part is proved. Second one is that X belongs to A closure if and only if distance of X from A is 0. Distance of X from A is 0. Okay. So B, X belongs to A closure if and only for any R greater than 0, open sphere about X with intersection A contains some point of A. If and only for every R greater than 0, there exists Y belongs to A such that D of XY is less than R. If and only if 0 less equal this, for every if and only if D of XY tends to 0 as R tends to 0. R tends to 0. If and only if D of XY approaches towards 0, if and only if infimum of D of XA or XY where Y varies in A is 0. Is 0. If and only if D of XA is equal to 0. So this is if and only if condition. This is if and only if condition. Now our aim is to prove to show distance between A closure and B closure is equal to D of AB. Distance between A and B. Now A is contained in A closure, B is contained in B closure. B is contained in B closure. This implies distance between A closure and B closure. This must be less equal to of AB. If I observe this diagram, this is my some A set. Okay. This is my some B set. And this is your A closure. This is your B closure. Then for this, from this diagram, D of distance between A closure, B closure must be less equal d of distance between A and B. Now to show d of AB is less equal d of A closure, B closure. This is our aim. Okay. For this, what we'll do? For this, we'll take 2 points from A and B, arbitrary 2 points from A and B. For this, for any A belongs to A, B belongs to B, X belongs to A closure, Y belongs to B closure, d of AB is less equal d of AX plus d of XY plus d of YB. D of YB. Is it clear? By triangle inequality. By triangle inequality, we will get this. If I take infimum, therefore infimum of A belongs to A, B belongs to B, d of AB, this must be less equal infimum of d of AX. A varies in A plus d of XY as it is plus infimum of d of YB where B varies in P. B varies in B. So we are proving C part. So I have to keep D. So for this now, infimum of DAB is nothing but distance between A and B. This must be less equal. Distance between A and X plus distance between X and Y is less equal d of A closure, B closure plus d of YB. Right? D of XY is less equal distance between A closure and B closure. Because X is member of A closure and Y is member of B closure. Y is member of B closure. So we'll get this one, D of A closure and B closure. Sorry, here we'll keep this d of xy as it is, right? And therefore d of AB is less equal 0 plus d of xy plus 0. Since X belongs to A closure, Y belongs to B closure. And by the previous part. So if X is member of A closure, then distance between X and A is 0. X and A is 0. So this is for any X belongs to A closure and Y belongs to B closure. This is true. Whatever that 2 points may be, this is true, and therefore d of AB, this must be less equal. There is no any restriction on choice of X and Y. Therefore, d of AB must be less equal infimum of d of XY, where X varies in A closure, Y varies in B closure, which is equal to d of A closure, B closure. So this is 1, this is 2. This is 1, this is 2. So from 1 and 2, from 1 and 2, we'll get d of AB less equal, d of AB is equal to d of A closure, B closure. D of A closure, B closure. Now we have to prove next part, D. To show d of A is equal to 0 if and only number of elements in A less equal 1. Okay. A contains at most one point. Okay. Suppose for this, if number of elements in A is greater equal 2, then for x not equal to y in A, d of xy is equal to r is greater than d of xy less than is equal to r is less than equal to supremum of d of AB, where AB value is in A, and therefore 0 is less than r less than equal to diameter of A. Contradiction. Therefore, diameter of A is 0 if and only number of elements in A must be less equal 1. Number of elements in A must be less equal 1. Then we have to show that if A is subset of B, then diameter A must be less equal diameter B. E, to show A subset of B implies diameter of A less equal diameter B. This is our aim now. For this, if diameter of A, B is less than diameter B, A, we'll assume that diameter B less than diameter A implies d of B1, B2 is less equal diameter of B is less equal diameter of A. Okay. For any B1, B2 belongs to A. But what is the diameter of A? This is supremum of d of A1, A2. A1, A2 belongs to A. This B1, B2 are in B. Diameter B1, B2 is strictly less than diameter of A. This must implies there exists A1 or A2 in A such that A1 doesn't belong to B or A2 doesn't belong to B. If all that points lies in B, then equality must hold. Equality must hold. Is it clear? Oh, इसकी भी कोई diameter B less than diameter of A is equal to this must implies there are some 2 points A1, A2 in A such that A1 must not be in B or A2 is not in B. This implies B is not subset of A. Contradiction. And therefore our assumption is wrong. Therefore our assumption is wrong. Now we have to prove diameter of A is equal to diameter of F. To show diameter A is equal to diameter of A closure. Now since A is subset of A closure implies diameter A less equal diameter of A closure. Diameter A closure. Is it right? Now diameter of A closure is equal to supremum of d of xy. D of xy, where xy belongs to A closure. This must be equal to supremum of d of xy, where xy value is in A, since for any A belongs to A closure, distance between A and A closure is 0. The points which are in A closure, which are not in A but are close to A, distance of that points from A must be 0. Must be 0. And that's why this equality must hold, and therefore this is equal to diameter A. This is equal to diameter of A. Is it clear? Now what to prove? F we have proved. Okay, we'll prove H first. Say. For xy belongs to A union B, for xy belongs to A union B. How I can write this? Case 1, if x belongs to A, xy belongs to A, or xy belongs to B, then both lies in A, then d of xy is less equal diameter of A or diameter of B. Implies d of xy is less equal dA plus distance between AB plus distance between diameter of B. Case 2, if I take x is in A, y is in B. If x belongs to A, y belongs to B. If I take these 2 points now, then d of xy, I can write this as less equal d of xa plus d of AB plus d of by. For A belongs to A and B belongs to B. In this way I can write. This is possible, right? This is less equal diameter of A plus distance between A and B, here we'll take diameter A plus the distance between AB, whatever that 2 points may be, plus diameter of B. Okay, and therefore if I take supremum of xy belongs to x belongs to x, y belongs to B is less equal diameter of A union B. Diameter A plus supremum of d of xy AB A value is in A and B value is in B. B value is in B. This is true for any 2 points. This is true for any 2 points. Okay. Sorry. D of AB plus diameter B. Right. For any A belongs to A, B belongs to B. I am taking point like that. And therefore, diameter of A union B. Sorry, D of xy is less equal. We'll keep this as it is. D of xy less equal this. For any A and B belongs to B. Therefore, D of xy is less equal diameter A plus infimum of D of AB, where A value is in A, B value is in B, because there is no any condition on A and B plus diameter of B, which is equal to D of A plus distance between AB plus D of B. For any x belongs to A, y belongs to B. This is case 2. From case 1 and 2, from case 1 and 2 implies D of xy is less equal to D of A plus D of AB plus D of B for any xy belongs to A union B. A union B, whatever that 2 points may be, and therefore diameter of A union B must be less equal diameter A plus distance between AB plus diameter B. Right? So thus H is proved. H is proved. Now we have to prove G. G for x belongs to A, y belongs to B. Y belongs to B. D of xy is the less equal supremum of D of AB, where AB value is in A union B, which is equal to diameter of A union B. Diameter of A union B. Okay. I by H. By H. D of A union B is less equal to A plus D of AB plus D of B. This is less equal D of A plus, now since A intersection B is not equal to phi, implies diameter of, distance between A and B, this must be 0. This must be 0, and this implies D of A union B, and these two implies D of A plus D of B. So with this, we have proved all the results related with distances and diameters. So with this discussion for distances between point sets, between two sets, diameter, we'll stop our session here. Good day. Bye bye.